Section 10.1, the chi-square distribution. In this chapter we'll be discussing a couple of new kinds of hypothesis tests which will require the use of a new probability distribution, and the distribution is called the chi-square distribution, and it's denoted chi, the Greek letter, with a square, and then some graphs are shown below. So just a quick comment about the chi. It's not chi, it's not chi, and it kind of looks like a fancy X, but best to look at the Microsoft version down here and kind of mimic that, but kind of a fancy X on one and then just a slash on the other. And then we're going to use this for some new types of tests that we're doing. So they're not going to be t-tests and they're not going to be z-tests, they're going to be chi-squared tests. So let's look at these chi-squared curves. So you might notice chi-squares have df's to them like t's do. They're not necessarily bell-shaped. In fact, they look kind of right-skewed, and some of them severely right-skewed, like this one with a df of 4, and others just a little bit right-skewed, like this df of 16. So let's go ahead and note some of the properties that are on those graphs right here. The total area under a chi-squared curve is always equal to 1. We're going to be using these to find probability, so the total area always has to be 1, and that's why the ones that are shorter are also wider, so that the area still balances out. And chi-square curves are right-skewed, and one of the important things to note there is that they're not symmetric. Symmetric and skewed are somewhat opposites of each other, so once we state we have a right-skewed graph, then we know it's not symmetric at that point. And that means that tricks that we used before, like using the left side of a graph to help us figure out the right side, aren't going to work anymore. And then chi-squared curves start at 0, and they extend indefinitely to the right while the height of the curve approaches 0. So chi-squared curves have a starting point. They don't go to negative infinity and positive infinity on the two sides. They start at 0 and then they go forever to the right. And that actually is why we draw a vertical axis in when we draw these, not because we care about the height so much, but just to mark off where the two axes intersect is where 0 is, and all these curves are starting from there. And then as the degrees of freedom increase, the shape of a chi-squared curve begins to look more and more like a normal curve. So that's true, and you can see that happening a little bit as we go from df equals 4 to df equals 16. It becomes less skewed and starts to look more bell-shaped. But even at a df of 16, it still does look right-skewed and not bell-shaped. And in order for this to really start to look bell-shaped, the df has to get pretty large, larger than we'll probably see on the problems that we're doing. And just another quick comment about the curve starting at 0. That actually makes sense if you think of the fact that they're called a chi-squared curve. You should be surprised if something that's been squared has a negative value to it. And not that this is terribly important for what we're doing, but chi-squared curves actually come from squaring z-scores and adding them together. So if you randomly selected 8 values from a standard normal curve and got those z-scores and squared them all and added them together, you'd have one chi-squared value from a df equals 8. So the df actually corresponds to how many of those z-scores have been squared and added together. Alright, so the mean of a chi-squared curve, it turns out, is equal to its df. And if you combine that with the fact that the distribution is right-skewed, then we can say that the peak of the curve will occur slightly before the chi-squared value, corresponding to the number of degrees of freedom. And showing you that in a visual way, what that means is if you look at a chi-squared curve and it's got a df of 16, then if you were to drop down from the peak on that curve, the mean of 16 would be just a little bit to the right. When a curve is right-skewed, rather than the mean being at the peak, it's a little to the right. If the df is 8, drop down from that peak, and the mean of 8 is just a little to the right. If the df is 4, you can drop down from that peak, and then 4 would be just a little bit to the right of that. And the only reason that's important is because we're used to z-curves and t-curves that have a center at 0. If we know that you drop down from the peak and move a little bit over, that's your df. That gives us a little bit of a sense of the numbering on these graphs, and it'll help us place our test statistics later on. So let me go ahead and show you just a little bit about what we need to know with these chi-squared curves for moving into the next couple sections. Primarily what we need to know is how to find the area to the right of a specific value. It's going to turn out that all of our tests that we do in 10.2 and 10.3 are right-tailed tests. So if we know how to find the area to the right of a value, we'll be able to find p-values. So let's find the area to the right of chi-squared equals 18.22 if the df is 11, and they've also asked us to sketch that. So when I'm asked to sketch one of these, I start off by drawing both a vertical and a horizontal axis, and then I start at the intersection of those. I go up fast and down slow to make a right skewed shape, and I don't worry about how right skewed it looks. I basically draw the same shape regardless of the df, and then I drop down from the peak, and then I move just a little bit to the right, and that would be the df, which in this case is 11. So that just helps me know where to put this 18.22. This is 0, that's 11, so 18.22 would maybe be right around here. If this is a t-curve or a z-curve, I would expect that to be way out to the right, but if the peak is near 11, then 18.22 is not too far out in the tail. And then they want us to find the area to the right of that, so I'm going to shade that in. This is what I'm looking for. And I'm not going to use normal CDF to do it because it's not a z-curve, and I'm not going to use t-CDF to do it because it's not a t-curve. So what I'm going to use to find that area is chi-squared CDF, and it works just like t-CDF. You put in the left boundary, 1822, the right boundary, which there isn't one, so we'll use infinity, and then the degrees of freedom, which in this case is 11. And then we can go to the calculator and find out what that is. So when you go to the calculator, chi-squared CDF is where you should expect it to be. If you go into the distribution menu, just like you normally would, you have your normal CDF and you have your t-CDF. And if you arrow down far enough, you'll find a chi-squared CDF. And then I can put that left boundary of 1822, the right boundary of infinity, and 11 degrees of freedom. And just kind of looking at the picture real quick before I press enter, there's a visible amount of area there, so I don't expect this to be one that comes out in scientific notation, but it's still kind of small, so it looks like maybe 5% or something like that. So let's press enter and see what we get. That seems about in the right ballpark. So 0.0766 is that area. And again, just looking at the picture, the total area under the curve is 1. I just have a small portion of that shaded, so for that area to come out around 0.0766 seems like a reasonable answer. Alright, let's just go ahead and try that again with another example. Okay, let's go ahead and continue on to part B of that question. We're looking at another area under a chi-squared curve. This time the degree of freedom is 6 for the curve, so I'll go ahead and draw in the curve first, and then we'll think about what they're asking us to find. So chi-squared curves are right skewed, so up fast and then down slower to create that longer right tail. Because of the right skew, if you drop down from the peak and move just a little bit to the right, that should be your DF, so I'll put the 6 here. And then they want to know the area to the left of chi-squared equals 3.055, so I want to put that on the picture. And I know the curve starts at 0, and this is 6, so 3.055 is right about in the middle, so I'll aim for that middle spot, label that as 3.055, and then I'll draw up from there until I hit the curve. And they want the area to the left of that, and typically that would be all the way to negative infinity, but we have to remember that on a chi-squared curve it starts at 0, so all the way to the left on a chi-squared curve means all the way to 0. So that's the area we want right there, and we will use chi-squared CDF to go ahead and find that. So what we're going to want to do is enter chi-squared CDF on our calculator. Our left boundary is 0, so that's where this shaded area starts, and then the right boundary is 3.055, and the chi-squared curve, like a t-curve, needs that degree of freedom, which would be 6. So that's the calculation we want to do on our calculator to find that area. So let's go ahead and bring the calculator in. So we go to the distribution menu. Chi-squared CDF doesn't show up on a lot of the calculators on the screen initially, but if you arrow down far enough, it will. So there's the chi-squared CDF. Left boundary is 0, comma, the right boundary 3.055, comma, the degrees of freedom, which is 6. So we press enter, we'll get that answer, but let's have a moment to think about what that will be. So because we're finding this area right here, I just want to notice that that's to the left of the peak, and it looks like it makes up for sure less than half of the area. And yet it is substantial. It's not just some little tiny sliver out in the tail. So maybe this would be somewhere around like 20% or so. Something that really measures up, but is definitely less than half. So to figure out what that is, we just need to press enter. And the calculator says that that area is approximately 0.198. And then it's a 0, but followed by an 8, so we'll round that up to a 1. And that would be our area. And that matches up with what it looks like on the graph, so I feel pretty solid about that. So the one part that we want to be a little careful with when we're doing chi-squared, and especially when we're doing area to the left, is to remember that unlike a t-score, our left boundary is not negative infinity, but it's 0. Alright, and then just a reminder of the structure that we used on this one and the previous question. The chi-squared CDF that we're using is found in the distribution menu, and you might need to arrow down to find it like I did. And the structure of that command is chi-squared CDF, lower endpoint, upper endpoint, and then you need to fill in your degree of freedom. Alright, so that finishes up working forwards. When we go on to do confidence intervals in section 10.4, we're going to need to be able to work backwards to do that. And we're going to use the command inverse chi-squared to find the area to the left, where we give the area to the left. And then we'll have to enter in the df, and that'll give us the boundary that separates that much area to the left with that many degrees of freedom. And that will be necessary for confidence intervals. So let's take a look at it. Let's find the chi-squared value with an area of 0.30 to its left if the degrees of freedom is 14. Alright, so first I'll start off with a sketch. With the chi-squared curves, I always basically draw the same right skewed curve. I don't worry too much about the df in terms of how skewed should it be, but I do drop down from the peak and move just a little bit to the right, and that would be the df, so that would be my 14. They want an area of 0.30 to my left, so 0.30 is less than half. If I drop from somewhere between the peak and here, I would expect like around half of the area, so to have 30% is almost kind of like that last one, maybe a little closer to the peak. And I'm wondering, what is this chi-squared value? So I'm trying to figure that one out. And I know that the area to the left of that, according to this, is 30. So that's 30, and I'm wondering, what is that boundary? So the structure on that is inverse. So that chi-squared that we're looking for will be the inverse of chi-squared, where the area to the left is 0.30, and the degrees of freedom is 14. So the way I write that down is very similar to what we did with inverse normal or with inverse t. We have that area to the left, which is common for both of those, and then a df just like for the t-score. And I'll show you how to do that on the calculator in a second, but let's go ahead and set up the other one, and then we'll do all of them on the calculator at once. So find the two chi-squared values that have an area of 0.95 in the middle with a df of 10. So if you think about this idea of a middle area, that's what we usually are working with confidence intervals. So this is probably going to be an important one for us as we go forward. So I'll draw that right skewed. I'll drop down from the peak, move a little bit to the right. That should be the df, which should be 10. I want most of the area, 95% of the area, to be in the middle, with just a little bit left on each side. So there's going to be a boundary over here somewhere, which I'll call chi-squared L for the left boundary. And there'll be another one over here, which would be chi-squared R, or the right boundary. And we're going to want to figure both of those out. Now the 90% that they were talking about there is in the middle, the 95%. So the total area of the curve is 1, so if there's 95% in the middle, then this little tail right here would be half of the leftover area. So just think about those calculations real quick. 1 minus 0.95 gives what's left over, 0.05. And then we'd have to cut that in half. So there's 0.025 on this right side, and there's another 0.025 over here. And one of the things you would always want to check with these area in betweens is if you add them all up, it should total 1. So you could check that on the calculator as well. Alright, and then let's go ahead and set up the structure of the inverse chi-squared to see how we would do that. When you want to get the chi-squared value on the left, you would do inverse chi-squared. You would enter in the area to the left, which is 0.025, and then you'd put the degrees of freedom, which is 10. Now when you go to do the chi-squared value on the right, what we did back with the t distribution or the z distribution, whatever this was, we just took the opposite sign for this one. But here we don't have any negative values, so opposite sign is not going to work. And we don't have symmetry either. Just the way I drew the picture, I think you can kind of see it's not the same distance out to both of those numbers, even from the 10. So we have to calculate them both separately. And the thing that we have to be careful with on this one is it's the area to the left, not the area to the right. So even though the area in the tail is 0.025, we need the area to the left. And there's two ways to think about that area. You could add up the areas on the left. So you could say I have 0.025 out there plus 0.95, whoops, plus 0.95 in the middle is 0.975. Or to get the area to the left of this, you could do 1 minus the area that is to the right. Either way, you get that the area to the left of this mark is 0.975. So I need to remember that when I go to the calculator. So this is going to be 0.975 and then comma 10 degrees of freedom. So once I get this going on the calculator, those are going to give me the boundaries that I need to answer both of those questions. But this is where we hit a little bit of a snag, because when you go to the calculator, what you'd want to do is go into the distribution menu, and there's your inverse normal, there's your inverse t. So you'd expect if you go down here a bit, you'd find the inverse chi-squared, but all this stuff that's here, there is no inverse chi-squared. So we're going to have to kind of talk the calculator into this one. So I'm going to show you the steps to make that work. We're going to use something called the solver, and the solver is in the math menu. So we're going to want to hit the math key. Let me exit out of here first. So get to your home screen, enter the math key, and then solver's all the way down at the bottom. So you can arrow down, you can also arrow up, it'll get there a little faster, but down at the bottom at number 0 is solver. And when you do that, it wants you to enter an equation. So the equation that we're going to do, and I'll explain the logic on this in a moment, is we're going to put chi-squared CDF. So I'm going to go into the distribution menu and choose that chi-squared CDF we just learned. And I'm going to give it a left boundary, a right boundary, and a degrees of freedom. So the left boundary is going to be 0 because that's the left edge of the chi-squared distribution. The right boundary is going to be the thing we're looking for, and that's a variable. So I'm just going to use an x for that. So I'm going to hit this xt theta key, and that'll fill that in with an x. And then we're supposed to put the degrees of freedom, so I'm going to use a d for that. So I'm going to hit alpha, and then this key right here because it has the green d above it. And then I'm going to end parentheses. So that's finding the area between 0 and x and d. And then I'm going to put a minus a, so alpha a, and that's going to represent the amount of area that I have to the left of x between 0 and x. And then I'm going to press enter. So what that does is it sets up a equation in the solver, and I can give 2 of the 3 boundaries and have it solve for the other one. So for example, on this problem right here, on this first one, our x value was the unknown. The area to the left was 30, and the df was 14. So if I highlight the d, that's the degrees of freedom, so that's 14. And the a stands for the area to the left, which is 30, so 0.30. And then this x is the one that I don't know. It's probably not the number 1. I can hit clear on that. In fact, we could think about it. You know, what is that roughly? That's 0, that's 14, so maybe this is around 10 or something in that neighborhood based on the picture that I've drawn. But the calculator will tell me what it is if I ask it in the right way. And the way we do that, to get x solved for you have to have the cursor flashing there. You have to hit the alpha key, and then let me move the calculator for you. Above the enter key in green it says solve. So if you hit the green alpha key and then you hit that solve key, it's going to think for a minute, still thinking, and then it fills it in. And what did we guess? That it would be around 10, and it turns out that it is 10.82, let's see, 10.82, and the next digit would be a 1 followed by a 4, so we'll stick with the 1. So 10.821. This whole part where we set this up is a little tricky, but it'll actually stay that way in your calculator. So then when you go to do other problems like these down here, you can just make the changes and then keep hitting the solve and keep getting new answers. So for chi-squared left boundary, we want, let's see, this is going to be our unknown, so I'll blank that out. I guess they're going to make me put some number there, so I'll just fill it in with anything. The DF is 10. The area to the left is 0.025. Now I just filled this in with any number, but if I highlight it and I hit the alpha key and then the enter key to do solve, it's going to think through with 10 degrees of freedom and an area to the left of 0.025, what is the chi-squared value? And it's telling me that it's 3.247. And then we need to do that one more time down here. DF is the same. Area to the left now is 0.975. Go back up to the X. Alpha, enter key for solve. Let it do its thinking. And it should come back with that answer, 20.483. So let's look at our picture and see if those two numbers make sense. So if this is 0 and that's 10, that this could be around 3, I think is reasonable. We don't draw perfect pictures, so this is somewhere between 0 and 10, closer to 0 than to 10, so a number like 3 makes sense. If I take this distance 10, another would be 20, and so we got 20.48. That sounds about right. Again, just a rough sketch, so that seems like roughly in the right neighborhood. If this is 10, that could be around 20 or so. All right, so filling in the calculator notes for you here, because that is the tricky piece on this. The first time you ever set this up, you have to go into Math and Solver. It's going to say equation 0 equals, and you complete that equation as chi-squared CDF from 0 to x to d, or with degrees of freedom d, and then minus a. The reason we do the minus a is if you added a to both sides, this would say a equals chi-squared CDF from 0 to x to d. So what we're telling the calculator is this chi-squared CDF goes from 0 to a mystery right boundary with a mystery degrees of freedom, and then this would be the area. The way the solver works, it has to have a 0 on one side, so we just subtracted that a over essentially. That's where the minus a comes from. So once we enter that equation in, we press enter. From now on, when you do any homework problems, test problems, that's going to be in there, and you just have to follow the steps beyond that. So we'll typically start these problems right here where that asterisk is. We'll enter our DF on the D line. We'll enter the areas to the left on the A line. We'll use our arrow keys to move to the X line, and then we'll press the alpha key and solve, which is above that enter key, and it will figure out that X. You give it 2 of the 3 values, it'll find the remaining one as long as you ask for it right. So unfortunately that's not built into the TI 83 or the 84, but we can still convince it to do that, and once we set it up, it's actually fairly easy to use on future times. All right, that wraps up section 10.1.